There are some kinds of important remarks or future works or concluding remarks in this section. These points will give you enough motivation to continue this path towards obtaining more complex Monte Carlo methods. For example, in these videos, I just explained the solution of the heat equation, the elliptic or the parabolic heat equation, but it's very interesting for us to extend the Monte Carlo method for the solution of the Navier-Stokes equation, which is the governing equation of the motion of the fluids. Now, this is the energy equation or the heat equation written for a moving media or for a fluid. As you see here, we have the material derivative, and in this derivative you have a velocity component which can be computed from the solution of the Navier-Stokes equation. The general algorithm is similar, but you have to discretize this equation. You see these two terms in the first side of the equation are similar to the heat equation, but this term is new. And then after the discretization process, you have again the coefficients of the neighboring particles and also the probability of remaining the random walk at its current position. Then you can continue. So the difference between the Monte Carlo method for the energy equation for a fluid and for a solid body is the different probability coefficients. In the final discretized equation, you can discretize the terms inside, the advective terms inside the material derivative using the 4-bar difference. Okay, the next point is the anisotropic form of the anisotropic means that the material, the different properties of the material is direction dependent. So when you are performing the random walk process, as you see here, the random walker is located at the center at point t, for example, and then it's going to find its way to the neighboring particles. So in our previous case, the random walker can go to the right, to the left, to the upper, and to the lower neighboring nodal points. But here, as you see, there is a fifth choice for the random walker to go, for example, to the upper right node. As you see, the direction of motion of the random walker is dependent to the material property, or the motion of the random walker is direction dependent. So this material is kind of anisotropic. So during the random walk process, you have to choose 5, for this case, of course, 5 intervals between 0 and 1. And as I explained before, based on the magnitude of the random walk, you may go to 5 directions. This is an example of them. For example, one anisotropic material may contain the direction dependence like this. So the property of the material is in a way that the random walker may go to the left and the upper node here. Okay, and no difference. So you can easily change your numerical code to consider the solution of PDEs for anisotropic materials. Okay, and the other point or the other challenge is the solution of the hyperbolic type equations, like the wave equation. The hyperbolic type equations have special behavior in their solutions, like the jumps or discontinuities, such as the shock wave in fluid mechanics, and also the behavior of the hyperbolic equation or the microscopic nature of hyperbolic equation is not random. So our described random walk process is not appropriate for the solution of such equations. There are some modifications of the random walk process for the Monte Carlo methods for the solution of the hyperbolic type equations to handle sharp discontinuities or jumps in properties. And the other challenge is the solution of the nonlinear problems in previous videos, I've emphasized on the linearity of the governing equation. So I told you that the coefficients should not be a function of the dependent variable. But if the problem is nonlinear, there are many active research fields for the solution of the nonlinear problem. As you know, the world is nonlinear. And the hybrid Monte Carlo method, the Monte Carlo method can be used in a hybrid manner with other deterministic, for example, numerical methods. And this is again to have the advantages of both deterministic and stochastic numerical methods. And there are some other branches or permutations of the Monte Carlo method. For example, the Monte Carlo based on the Green's function, or based on the walk on a sphere process, or the Monte Carlo method after rewriting the PDE as an integral equation. So you can first convert the partial differential equation to its equivalent integral form, and then use the Monte Carlo method.